Okay, let's just jump straight into this explainer. Today, we're diving into the completely invisible but incredibly high-stakes world of embedded systems. You might not always see them, but these microcontrollers and IoT devices are literally humming away in the background of our entire day-to-day lives. We're talking about everything from the anti-lock brakes in your car to the smart sensors wired into your home. But because we rely on them so heavily, we really have to ask a serious question about system reliability and automatic recovery. I mean, what exactly happens when the computer brains behind these mission-critical systems encounter an error and just stop?
So picture this terrifying scenario. You've got a remote, headless system that completely freezes up, and there is absolutely no human around to press the manual reboot button. Imagine a multi-million-dollar satellite orbiting the Earth in the freezing vacuum of space. It's a totally headless environment, right? No monitor, no keyboard, and for sure no IT tech floating by to just turn it off and back on again. If the software running that satellite locks up, it is entirely on its own. And that brings us to a really crucial concept known as a silent failure, or a kernel panic. Basically, this is a permanent failure state where just one unhandled software bug, or an infinite loop, causes the entire system to permanently stop working. The system just goes totally unresponsive. It doesn't even necessarily power down, it just freezes, permanently trapped in a deadlock. Without some kind of automatic way to heal itself, that incredibly expensive satellite basically becomes a highly engineered brick. To understand how engineers actually solve this massive problem, here's our roadmap for today's explainer. First, the threat of system failure. 2. Meet the Watchdog Timer. 3. How the Watchdog works. 4. Coding the Watchdog. And finally, 5. Mission-critical applications. Okay, jumping into Section 1, the threat of system failure. This is all about when machines simply cannot afford to fail silently. Let's establish just how catastrophic an unhandled freeze actually is. The reality here is that many embedded systems simply do not have the luxury of a silent failure. When you're dealing with devices inside a patient's body, like critical medical equipment, or automotive control units managing a car speeding down the highway, or those deep space probes we mentioned, an infinite loop is practically a death sentence. You can't just walk up and unplug them. A single, tiny, unhandled software bug could halt the entire operation. That's exactly why a self-healing mechanism isn't just a nice-to-have. It's absolutely non-negotiable. Moving on to Section 2, meet the Watchdog Timer, the ultimate hardware solution for self-healing. The way engineers solve this silent failure problem is actually brilliantly simple, and it lives physically inside the microcontroller itself. Think of it like a literal watchdog. You've got your firmware, right? And this firmware has to constantly pet or feed this watchdog by giving it a bone. As long as it keeps handing over that bone on schedule, everything is great, good watchdog. But if the firmware freezes up and forgets to feed the dog, well, the dog gets angry and bites, which forces a violent system reset. It's the perfect metaphor for self-healing. If the software stops responding, the hardware watchdog steps in and automatically reboots the whole thing so it can come back online safely. Section 3, how the watchdog works, the mechanics of a forced reboot. Let's look under the hood and see how this timer actually pulls off a forced reboot without any human intervention. The timer operates in 3 totally relentless phases. Step 1 is monitoring. The watch time timer is just continuously running in the background, expecting a regular refresh signal from the microcontroller. Step 2 is timeout detection. If the microcontroller fails to send that refresh signal within a set time, say because it froze, the watchdog doesn't stop. It just keeps counting until it hits its absolute limit. And then step 3 is the reset. The second it reaches that timeout, the watchdog fires off a reset signal to forcefully restart the microcontroller and restore normal operation. If we peek at the underlying architecture, it boils down to a simple, continuous pulse exchange between a counter loop and the main controller. A primary clock provides the heartbeat to both the controller and the watchdog timer. Now, the controller is supposed to consistently send a recert command to the timer, but if it doesn't, that timer hits its timeout limit and immediately routes a reset signal straight back into the controller. It is an inescapable loop of accountability. Section 4, coding the watchdog, implementing the metaphor in C code. So, how do software engineers actually write the code to pet the dog and keep this timer happy? Going into a standard C code implementation, it's actually pretty straightforward. Right at the top, the engineer enables the watchdog with a set timeout limit, let's say 5,000 milliseconds, which is 5 seconds. Then the code enters a while-one loop. This is a continuous, infinite loop where the system's main tasks actually run, like task 1 and task 2. But here's the kicker. Immediately following those tasks is the all-important refresh Watchdog command. As long as those main tasks finish their work in under 5 seconds, the Watchdog gets refreshed, the timer resets, and the loop starts all over again perfectly safely. But this is the absolutely crucial point. If that refresh command isn't called before the timeout limit expires, a violent hardware reboot is completely unavoidable. Think about it. If task 1 hits a bug and gets stuck in an infinite deadlock, the code is never going to reach that refresh Watchdog line. The hardware timer will blindly tick down from 5 seconds to 0, and then bam, it resets the entire system to clear out the error. And that brings us to Section 5, Mission-Critical Applications, where watchdogs live in the real world. Let's look at how this incredible self-healing technology is deployed across massive industries. Watchdog timers are basically the unsung heroes across 4 major quadrants of modern engineering. You're going to find them embedded deep inside automotive dashboards, real-time motor control boards, mission-critical medical monitors, and remote tablet systems. They all rely heavily on this invisible watchdog standing guard. Let's break those down really quickly. For remote systems, think space probes and remote sensors, there's zero chance for a manual reset, making the watchdog essential for survival. For mission-critical setups like hospital medical equipment, the system has to recover from a failure instantly because human life is on the line. In real-time control, like motor control and factory automation, watchdogs prevent devastating physical crashes on the assembly line. And finally, in safety-critical systems like automotive and aerospace, they guarantee reliable, safe restarts even while you're actively traveling in the vehicle. So, tying it all together, the Watchdog timer is the vital system glue. You can think of the software driver as a robotic arm that has to periodically deliver a mechanical kick or a ping to a ticking hardware counter. That counter is constantly relentlessly ticking down toward an unmaskable system reset. If the software environment hangs and misses that vital kick, the hardware violently reboots the system to restore function. It really is the ultimate failsafe against a permanent kernel panic. Which leaves us with this final, kind of fascinating question to ponder about the ultimate limits of autonomous, self-healing systems. If watchdog timers are the absolute last line of defense keeping our most critical remote machines alive, who or what is watching the watchdogs to make sure the hardware itself doesn't fail? It's a pretty wild testament to the sheer amount of engineering required to keep our modern, interconnected world running smoothly. Thanks so much for joining me on this explainer, and keep asking those great questions.